I'll be presenting some notes on phase space in statistical mechanics. Let's start with the concept of phase space, specifically for a single particle known as mu space. In classical mechanics, if we want to completely specify the state of a particle at any given instant, we need two sets of coordinates. First, we need its position, given by the three spatial coordinates x, y, and z. Second, we need its momentum, given by three momentum coordinates px, py, and pz. Mathematically, we can combine these to imagine a six-dimensional space where all six variables are independent. This 6D space is what we call the phase space for a single particle. Now let's define a volume element in this space. Since it's a six-dimensional space, the volume element will be denoted by d gamma. Is simply the product of differentials of all coordinates dx, dy, dz and dpx, dpy, dpz. We can group these dx, dy, dz forms the volume element in the ordinary position space, which we call dv, and the dpx, dpy, dpz forms the volume element in the momentum space, d tau. So the phase space volume element is the product of the spatial volume element and the momentum volume element. Remember, when we talk about a single particle, this is specifically called the mu space. Moving on, let's consider a macroscopic system containing a large number of particles. Suppose this system has f degrees of freedom. To specify the state of this entire system, we need f independent position coordinates, denoted by q1 through qf, and f independent momentum coordinates p1 through pf. Therefore, the total number of independent variables required is 2f. This brings us to the definition of gamma space. This conceptual space has 2f dimensions. To give you an idea of the scale, if we have a simple system with 3 degrees of freedom, the phase space is 6-dimensional. But if we have 10 degrees of freedom, it becomes 20-dimensional. For a real gas with Avogadro's number of particles, this dimension is enormous. Essentially, the gamma space is the superposition of all the individual mu spaces of the particle. We can treat it as an Euclidean space with 2f rectangular axes. Similar to the mu space, we can define a volume element in the gamma space. It is the product of all the position differentials and all the momentum differentials. Using product notation, we can write this compactly as the product over k equals 1 2f of dqk dpk. A single point in this huge 2f dimensional space is defined by the set of coordinates qk and pk. This unique point represents the complete dynamical state of the entire system at one point or one instance. We call this a phase point or a representative point. If we are dealing with a gas, they are sometimes called to as the G points. It is crucial to remember that this entire framework is purely classical concept. As time progresses, the state of the system changes. The position and momentum of particles change according to the laws of mechanics. Consequently, the phase point moves through the phase space. This path traced by this moving point is called a phase trajectory. This path is deterministic and governed by classical mechanics. How do we determine exactly where the phase point is at any point? We use the Hamiltonian's canonical equation of motion. The time derivative of position qk is the partial derivative of the Hamiltonian h with respect to the momentum. The time derivative of the momentum is the negative partial derivative of the Hamiltonian with respect to the position. Here the Hamiltonian over q and p is the total energy or the Hamiltonian of the system. An essential geometric concept here is the energy surface. For an isolated system, energy is conserved. This means hqp equals E is a constant. This condition defines a surface in the phase space. Since energy doesn't change, the phase point must always stay on this specific surface. It cannot jump to another energy surface. If the energy has a small uncertainty, say between E minus delta by 2 and E plus delta by 2, then the trajectory is confined within a thin hypercell bounded by these two energy values. Let's make this concrete with a simple example. A linear harmonic oscillator, the total energy E is the sum of the kinetic energy P square by 2m and the potential energy 1 by 2 alpha q square. Here m is the mass, alpha is the force constant, q is the position, and p is the momentum. Solving the Hamiltonian equation for the system gives us the sinusoidal solutions. Positions q oscillate as the sine wave and momentum p oscillates as the cosine wave, since it's the derivative of the position. We can normalize this by the maximum amplitudes q0 and p0. If we square the normalized equations and add them up, we use the identity sine square plus cos square equals 1. This gives us the equation q square by q naught square plus p square by p naught square equals 1, which is basically the equation of an ellipse. So, for a harmonic oscillator, the phase trajectories are ellipses centered at the origin. A key property to note is that the phase trajectories can never intersect. Why? Because if they did, the intersection point would represent a state from which the system could go in two different directions. That would violate the deterministic nature of classical mechanics. Given a state, the future is uniquely determined. Now we move to the statistical mechanics proper. Here we define the density of phase points denoted by rho. Imagine we have an ensemble of many identical systems. The number of phase points per unit volume in the phase space gives us this density rho. It specifies the statistical state of the system. Mathematically, if we take a small volume element d rho and count d del n phase points inside it, the density rho is the ratio del n by del gamma. This is known as the distribution function or the probability density function. It tells us how likely we are to find the system in a particular state. Rearranging that definition, the number of phase points in a volume element is simply the density times the volume. For a system with f degrees of freedom, this density function rho is a function of all f position coordinates and all f momentum coordinates. Since the points are moving, the density at any fixed location in the phase space can change with time. So rho is explicitly a function of time t as well. We write this dependence as gamma q1 to qf and p1 to pf along with the time t, or more compactly, rho of qk, pk, and t. Just to recap, the volume element in this context, it is the product of all positions and momentum differentials written compactly using the product symbol pi. Substituting this volume element expression, the number of points del n is rho times the product with all the dqk and dpk. To find the total number of phase points n in the entire ensemble, we integrate the density over the entire phase space. This is the two-dimensional integral. It sums up to the probability densities over all possible states. Often it's easier to work with probabilities directly. For this, we will use the normalized density distribution function rho n. We define rho n simply as the density rho divided by the total number of points n. This normalizes the function so that it represents a probability rather than a raw count. Physically, rho n represents the probability per unit volume of finding a phase point at a specific location. It answers the question, what is the chance the system is in the specific state? If we integrate this normalized function over the entire phase space, we must get 1. The math is simple. The integral of rho by n pulls out the constant 1 by n, and the integral of rho is just n, so we get n by n equals 1. This result of the integral of rho n d gamma equals 1 is the normalization condition. It signifies certainly the probability that the system exists somewhere in the phase space is 100%. After understanding the concept of phase space, phase points, phase trajectories, and the density distribution function, we are now ready to discuss a very important theorem in the classical physics, the Liouville's theorem. In this section, we will explore the theorem states, what the theorem states, how to prove it, and its physical significance. The dynamical state of a system is represented by a phase point. As this point moves according to the Hamiltonian equation, the density rho of the points changes. Liouville's theorem aims to find the rate of this change. This theorem has two parts. Part 1, the principle of conservation of density. It states the total time derivation of the system density is 0. This means if you sit on a phase point and move with it, the density of the points around you remains constant. Part 2 is the principle of conservation of extension. It states that any arbitrary volume del gamma occupied by a group of phase points remain constant in size as it moves through the phase space. The shape might distort, but the volume is conserved. To prove the first part, let's visualize the flow of these phase points. Consider an arbitrary volume V in the phase space enclosed by a surface S. The points are moving with velocity V. We want to calculate how many points are flowing out of this volume through a small surface element ds. The rate at which phase points flow out is given by the surface integral of the flux P rho V. The rate of decrease of points inside the volume is the negative time derivative of the integral of rho. Since the points are conserved, the outflow must equal the rate of decrease. We use Gauss's divergence theorem to convert the surface integral into a volume integral of the divergence. Equating the two equations, we find the integral of the divergence of rho v plus the partial derivative with respect to time of the rho must be 0 for any volume. This implies that the integrand itself is 0. This is the continuity equation. In our 2f dimensional space, the divergence involves derivatives with respect to all q's and p's. We expand the term the divergence of rho v using the product rule. Here is the clever step. We substitute the Hamiltonian's equation for Qk and Pk, we find that the partial derivative of Qk with respect to Qk, like the first derivative, is exactly the negative of the product differences. This means the terms involving the derivatives of velocity cancel out completely. We are left with a simpler expression involving partial derivatives of the Hamiltonian and the density rho. This specific combination is also known as the Poisson's bracket of h and rho, denoted in the third bracket of h and rho. So the continuity equation becomes the Poisson's bracket plus the time derivative of rho, which is equals to 0. Finally, recall the definition of the total time derivative. By chain rule, it is the sum of partial derivatives times the rate of change of coordinates, plus the explicit time derivative. Substituting the Hamiltonian's equation again, we see that this is exactly equal to the Poisson's bracket of h and rho plus the time derivative of rho. Comparing our result from the continuity equation, we see that this entire sum is equal to 0. Therefore, d rho dt equals 0. This completes the proof of the Liouville's theorem. The density of phase points in the vicinity of a moving phase point is constant in time. Now we prove the second part. Conservation of extension. Consider a hypervolume del gamma in phase space. The number of phase points n in this region is the product of density rho and the volume del gamma. Since points are neither created nor destroyed, n is constant, so its time derivative is 0. Substituting n equals rho del gamma and using the product rule, we get the two terms, one involving the rate of change of density and one involving the rate of change of volume. From the first part of the theorem, we already know that d rho dt equals 0. This means the first term vanishes. Since the density rho is not 0, the rate of change of volume del gamma must be 0. This proves the second part of the theorem. This brings us to the physical significance of the theorem, often called the principle of conservation of extension in phase space. It tells us that while the shape of a region of phase points might change as it evolves in time, its total volume remains strictly constant.